friend Amit Prashant, Prof Amit Prashant. Actually, I have not directly interacted with him, but I know he was at IIT Kanpur. Rajesh, your erstwhile colleague from IIT Kanpur, and I know that he is specialized in digital image analysis of fracture test and all. When I visited IIT Kanpur, they have shown, when I went to the lab, Professor Amit, they have shown the setups which we have developed and which are being used and all. So, and now I think over the past, what I can say about when you moved, Professor Amit Prashant?
2010.
So almost time runs very fast. For the past 10 years, Professor Amit Prashant is at IIT Gandhinagar, and for some time he was acting director IIT Gandhinagar and holding the responsibility and holding the mantle for some time till the same Professor Surendra Jain is reinstated. And currently, I think Professor Amit Prashant is the Dean Research and Development of IIT Gandhinagar. So Professor Amit Prashant is going to deliver, the lecture on the investigation of instabilities in granular media and the numerical simulation. I think this is, one of the topics. Still, I think Arya Das is also investigating in IIT Kanpur.
Try to finish before 20 minutes.
I think I'm seeing some 30 delegates are there. I think we welcome the delegates also. Yes.
So, hello friends, I'm going to talk about this granular mechanics a little bit, mainly the focus on instabilities. The work is mainly coming from Dr. Debayan Bhattacharya's work at IIT Gandhinagar. He finished his PhD about 1 year back, 1.5 years back. And right now he's in with Professor Wu in Boku, which is another very prominent group in this area. And also some work has come from earlier, one of my earlier student and now faculty in IIT Mandi, Professor Maushmi Mukherjee. So what is this all about is you will see some glimpse of that in this video. I hope you are able to see that video. The message from this is it triggers suddenly, but there are various modes of instabilities that get mixed. It's not one mode that we generally refer to as strain localization, but multiple modes go into mixing with each other, one after another, and then that evolves how the material is going to behave after failure. What we often interpret as failure is actually much later than when failure happened, and that means it has become boundary value problem when we talk about the laboratory test. So in a way, in many cases, the calibration of material models or solving real life problems can be problematic. And this has been a problem for a long time. A number of groups in the world are working on these issues. And some of those examples I'm showing here one by one. It applies to not only landslides that you saw in the first one, but also many cases. A good example of this instability and mixing of modes can be lateral spreading, which is a multi-mode in the sense of liquefaction as well as flow of the material, or you can say displacement of the material with time. So there are other examples of that. So landslides is one, slopes and retaining structures, failure behind them is another one. And then you have liquefaction and its impact on different structures. How do you simulate that in a proper manner? Earthquake faults can be 1 meter, 2 meter, 3 meters sometimes. And they are quite, you can say, narrow band deformations. And their influence on structure is a lot of interest today. Avalanches, debris flow is what you saw on the slide itself. Pavement cracks in the subgrade is another good example of that. Simulating that is a challenge always. Borehole instability in oil sector has been a topic of discussion for a long time. So these are some examples. There are many more examples where large deformations and cracks and discontinuities can become a challenge and in simulation, and how do we handle those. So as I was mentioning, there are multiple modes. Some of the modes are given here. Bulging of the samples that you see, Here, maybe I'll pull up the pen, laser point. Right. This kind of thing you may have seen, buckling of the samples can happen. And then shear band and strain localization is what most commonly or most researched topic nowadays. Liquefaction is more researched from the applied side right now, but from the science soil mechanics side, there's a lot of unknowns still in that area. So these are some of the modes, and there are many more modes that you can talk about. Some examples are shown here. All these modes go into deformation response of a real life structure. If you want to simulate that properly, then you have to understand that. Why is this so complicated, or why do we need to worry about this? A little bit of glimpse of that is given here. That the soil can behave like a liquid here on the top left. And you saw in the landslide itself, it was flowing like a liquid almost, right? And on the right side, you see a sandcastle, which is more like a solid, but very fragile, less of deformations, you can say, yes, strength in there, with less confinement. It can also behave like a gas that you see at the bottom, for example. And when you have failures, you have some of that in various forms. When we look at an element in a problem, boundary value problem, or like, for example, here, soil below foundation, if I look at very small zone and assume that as a single element, then in that, the response, what we observe in the lab, that will be expected to be similar, but it may not be actually, right? So if I look at the failures when it happens and look closely into that, then I'm going into the scale of, you can say, a couple of millimeters. And if I go further down, I'll be reaching the scale of particles. And now the dynamics, or the way things happen, will be understood in a different way when we look at the single element versus when we look at a couple of millimeters. Like, for example, here, finite element simulation is showing that there is a lot of heterogeneity that has developed in a local region. And when heterogeneity has developed, can I interpret that as the strength we measure from the sensors at the top and the cell pressure? Not really. The stresses at the local locations will be very different. And the fluid flow may happen there as well, as densities are changing. So that means under undrained condition also, when we assume there is no flow of water, actually there is a flow of water, but it is local. And as you can see on the particle scale, that is possible as well, because as the particles deform, they collapse, they form new blocks, and the water will be moving locally from one zone to another zone. And all that becomes a complex phenomena where we can look at it more closely with DEM type simulations, discrete element modeling, but that is expensive business. Real life problem solving with that is going to be very challenging. So in that case, we want a solution at continuum level where we can still analyze and solve these problems, these issues, or incorporate these aspects into the behavioral response or prediction of the response for boundary value problems. So in a way, the combination of continuum elastoplastic framework with some, you can say, element type testing or boundary value problem, either of those, and the knowledge that we gain from discontinuum granular framework, discrete element modeling kind of concepts, and also variety of experiments that we can do with the understanding of different stress paths and different combinations of stresses, how they impact on the overall response. That is going to connect these two, discrete element and continuum as well. With image analysis, that becomes a little bit more possible to have deformation field measurements and understand how the deformations or the failures are evolving in different zones of the structure or soil element. So with this, you can say different domains of investigation, we have been trying to investigate how to get this problem to a level where we can easily implement in a software where we can have boundary value problems solved with realistic failure mechanisms. So that is the overall objective of this overall research. What we have recently done is developed a plane strain system, which is with flexible boundaries. And we got some tests done from that. And at the same time, or rather before that, we started working on some, you can say, simulations of plane strain problems. So most of the geotechnical problems are plane strain, we know. And it's easier to look at these problems in two-dimensional than three-dimensional. So that is where the motivation was to first focus on plane strain problems. So we did some with Maushmi's effort initially, and then Deban did a lot of work on that. We looked at different mathematical formulations, constitutive equations, how we can predict the bifurcation, using the bifurcation method, you can say how we can predict what happens with different modes of failure. Or instability, you can say. So, and when we do simulation, how these things are going to impact our simulations. So the simulations we are doing today, and we assume that they are correct, are they really correct? That is the question. So we looked at different undrained as well as drained modes with the liquefaction and localized instabilities and so on. If you look here, the only thing I want to point out here is you look these triangles and these circles. So if I do kind of, you can say, large deformation analysis versus small deformation analysis, the formulation that we use in finite element codes. So when we do small strain deformation simulation, we will not see these kind of triangular type instability modes. What we eventually see is only these circles. So that's where the failure appears to be in this as predicted by the response. But actually the instabilities can start well before that. And another point to note here is instabilities start in hardening zone itself. So quite often we say that when you see softening, there is an instability. But actually that is not necessarily true. And why is it important? The moment these things, these instabilities develop, you will have heterogeneous element response, or you can say heterogeneities have developed. So a single element will still behave as a homogeneous response, but actually it may have already caused problems. And that creates mesh dependency. And that is where I will show some results further. So that is the main message from this slide. Beyond that, you can see large deformation response and small strain deformation response. Even the band inclination angle, the shear bands that develop in a simulation of a single element are quite different. And that is where the small strain deformations have to be understood with a pinch of salt, that we have some approximations involved in those. Similar observations we had with undrained instabilities as well, where, however, the solid fluid instability became more prominent, as you can see with the star sign there. These are followed by some other instabilities, like, for example, shear banding. Now, what is solid fluid instability is one of the liquefaction mode, you can say, something like that. So these keep on happening whether they reach another stable state or they continue to become unstable. And that is where the question is. So if you look here, in some of the cases, it is going to higher and higher level of stresses in this stress path, whereas in another case, it is going to soft location, what you understand as a liquefaction. So, but instability had been triggered in all of them. But some after instability gone into the you can say more of dilative mode, and some of those got into contractive mode and failed. So we also did some coupled analysis of coupled transient analysis, understanding that when we model the fluid flow within the element, then we will have the, you can say, locally drained but globally undrained condition. And in that, the triggering of instabilities is possible, some of the modes, or you can say it is earlier than what you generally observe in other simulations. So one message that comes from here, if you want to simulate instabilities properly, and especially under undrained conditions, then it is better to do transient analysis than the you can say steady state type regular analysis that we do at small strain formulation. So that was one key finding from that. Another aspect is a way of triggering instabilities into the soil domain is introducing some kind of property perturbation. So material properties varying from location to location. And that is the reality in the field as well. So when we look at that, what we saw is two things. One is intensity of perturbation has some impact, and there is a way we have to worry about it, and there is a way to handle that also. And second aspect is when you have these instabilities evolving, there will be mesh dependency. So when we look at the mesh dependency in while doing FEM simulations and convergence, we generally focus on this region at the lower, but not so much at failure, assuming that failure will be okay. But actually, it is not true. So when we have instabilities, actually it can be predicted at any level, depending on what is the mesh size that you're using. And that is now known as a pathological mesh dependency of small or large deformation. Both have this problem. One solution to that can be that we use rate-dependent models. So rate-dependent models has a time scale captured in that, and that helps in you can say handling this mesh dependency issue. Another is you do mesh convergence for each perturbation formulation simulation that you're doing. So in each case, we have to do mesh convergence. It's not like that I have done once and then I can simulate 10 more problems with that. And with those particular perturbation intensities that we have incorporated for triggering the instabilities. And I'm talking in reference to finite element simulations. Right? So with what you see here is the result of that in a way that there can be contractive and dilative bands developing in the soil element if you simulate. And also, you can say, if you notice, a sudden change in the response is observed when such kind of instabilities develop in the global response. So the measurements at the boundaries. And all this is possible when we do transient type analysis and not steady state type analysis, what we 99.9% problems we solve. And with, we have to assume that it is locally drained and globally. So these are some keywords that you have to keep in mind. What it shows is instability developed, then there is a flow of water all around, fluid is flowing internally, but globally there is no flow. So we developed a rate-dependent model also, which is recently published, and with that we did some simulations as well. With those simulations, the results come out to be much better than what we can generally expect. Even if the material as such is not expected to be rate-dependent or not expected to be, the problem is not expected to be rate-dependent as such. Still, for simulation purpose itself, it becomes important to use rate-dependent models if you're doing finite element simulations to capture the instabilities properly. So in a way, what we want to say is this discontinuum world is the way to go, but for only research. When we go to the real life problems, it is difficult, but insights from grain scale analysis is very useful. This is the setup we developed here at IIT Gandhinagar, which is a true coaxial system and all fabricated here itself, and with plane strain arrangement, you can say, if you see a glass plate at the top. So we compared the results from discrete element simulations from Devine's work with the experiments from this plane strain device with flexible boundary, and we found quite a comparable results. These are some of the observations and results from the analysis. This is the last slide, so there is some, I'm finishing in time. So what message I want to give here is simulating instabilities, understanding different modes, and you can say solving real life problems with you can say more realistic simulation of at failure locations with some examples that I gave in the beginning is challenging. Efforts are being made at micro level to continuum level to applying that to field problems in all that sectors, and the research is on right now. I'm hoping that with a lot of effort that we are making and several other groups are making, we'll be able to have much better solutions in the future. So with that, I'm stopping it. Hopefully, you have got the sense of what we are doing, a glimpse of that, and I'm happy to take any questions.